Howdy, I'm Matt Cleveland, and this is my research presentation for my project Finding Vacancy Formation Energy in Amorphous Silicon. I'd like to thank my sponsors, the Department of Energy and the National Nuclear Security Administration, for funding this project, as well as the Center for Research Excellence in Dynamically Deformed Solids. And I'd also like to thank the online O-REU program at my home institution of Texas A&M for hosting the summer research experience. I'd also like to thank my collaborators, my mentor Dr. Michael Dimkowicz, as well as Dr. Ping Cheng for providing technical support. I would like to begin by defining vacancy formation energy. Vacancy formation energy is defined as the energy it takes to remove an atom from its place in a perfect crystal, creating a vacancy defect. Now, for a perfect crystal, this energy should be positive, meaning that it takes energy to remove the atom from its spot in the perfect crystal and move it somewhere else. Now, a quick note on the terms vacancy formation energy and the related term atom removal energy. Atom removal energy is simply the change in energy between these two structures. Taking the energy of the structure with the vacancy and subtracting the initial energy of the perfect crystal. However, vacancy formation energy takes into account the energy of the atom, as it has not simply disappeared, but rather it moves to someplace new. And so vacancy formation energy has this term, the energy of cohesion, which looks at where that atom goes. It looks to see what the new energy for that atom is. Now, the goal of this project is to look at the vacancy formation energies as it pertains to amorphous silicon. So amorphous silicon differs from crystalline silicon in that crystalline silicon is composed of periodically repeating unit cells, meaning that all the atoms are identically arranged in space. There's a pattern and it's like a three-dimensional tiling. However, for amorphous silicon, there is no periodically repeating base structure. All the atoms are uniquely arranged within their space. And thus, for crystalline silicon, all the atoms have identical positive vacancy formation energies. However, for amorphous silicon, the vacancy formation energies differs as all the atoms are differently arranged. And thus, these differing vacancy formation energies may be negative. So the goal of this project is to determine whether or not amorphous silicon has negative vacancy formation energies in its structures. So our method for this is to use atomistic simulations to study the vacancy formation energies for different structures of amorphous silicon. So first we have to obtain structures of amorphous silicon. We do this through taking crystalline structures of amorphous silicon and raising the temperature until it liquefies and then rapidly cooling it to then obtain amorphous silicon structures. Then we take our amorphous silicon structure and we find the atom removal energy for each atom in the amorphous silicon structure. So this process involves us taking an amorphous silicon structure, selecting an atom in it, removing it, finding the new energy, and then comparing that to the original energy. So we'll do this process for each atom in the structure. And thus we have a list of all the vacancy formation energies for each atom in the structure. We select the lowest atom removal energy from that list, and we remove it from the structure, and that becomes our new input, and we repeat this process. We do this to get a sense for what happens as we remove atoms from the structure. And what we're hoping to see is, do the negative vacancy formation energies dissipate, or what happens? So perform the above algorithm on amorphous silicon structures of 1,000 atoms, and we obtain the following histograms. And so initially what we have is a histogram that looks as follows. You see most of it, all of it is less than the vacancy formation energy for crystalline silicon, which is right about there. It's an asymptotic limit. However, there is a tiny tail that includes negative vacancy formation energies, which is what we're looking for. And as we repeat this process, removing atoms from that negative vacancy formation energy tail, what we see is that the negative vacancy formation energies after 700 iterations become incredibly negative by an order of magnitude, and that there's only a relatively small remainder with positive vacancy formation energies. So to better understand what is happening, we decided to run the algorithm on crystalline silicon. And so what we see is we start off with a very normal crystalline silicon structure with a single vacancy. But as we remove more and more of the atoms, we see that there emerges this region with negative vacancy formation energy. And this region of amorphous silicon emerges as more and more atoms are removed. So this is in contrast to the expectation of the algorithm, which would have been that it would have contracted back to crystalline silicon. Instead, we see that amorphous silicon, this unordered structure, emerges as we remove more and more atoms, and we get more and more negative vacancy formation energies. So this is the key graph for the presentation. This is a graph of the minimum atom removal energy versus the cohesion energy for each of the various iterations in the simulations. So what we have is very simple, as atom removal energy is just the difference between the structure with a vacancy compared to the initial energy of the structure. And cohesion energy is the energy per atom in the various structures. Now, what we're interested in is the vacancy formation energy. And now vacancy formation energy, as you recall, is related to this relationship between the cohesion energy and the atom removal energy. And so thus there's various definitions on what is vacancy formation energy depending on where we think that the atom is going. If the atom goes to a crystalline silicon structure, then it is defined as the cohesion energy of diamond crystal silicon, or 4.67 electron volts, which would be a straight line. However, if it goes to a spot of amorphous silicon, then it is that particular cohesion energy. Now, so that would be translating this line, and it would still be vertical. However, this is the most liberal definition of cohesion energy, or of the cohesion energy, which is that the cohesion energy is the cohesion energy of the structure. This is a plot of the one-to-one relation, meaning that anything on this side has a positive vacancy formation energy, anything on this side has a negative vacancy formation energy. And so of the structures we analyzed, we see that crystalline silicon is the only thing that has a clearly positive vacancy formation energy. Conversely, all the amorphous silicon structures are mainly on the negative side of this line. There's a few outliers that are close to the line, but keep in mind, this is the most liberal definition, giving it a chance to have positive vacancy formation energies. And these are just a few isolated examples. In most of the other cases, we see that once they become amorphous silicon, we have negative vacancy formation energies. So what can we conclude from all of this? We found that crystalline silicon does indeed have positive vacancy formation energies as expected for a crystalline structure. However, the tested forms of amorphous silicon did have negative vacancy formation energies. So, this is interestingly enough corroborated by an experimental observation that shows that amorphous silicon continuously relaxes into non-amorphous forms of silicon as atoms with negative vacancy formation energies perhaps move to crystalline forms. So further work is required to answer the question of what happens to amorphous silicon as we remove atoms so that we can better understand this phenomenon of amorphous silicon having negative vacancy formation energies. Thank you so much for listening to my presentation. Have a wonderful day.